In this problem, we need to optimize z given this constraint. First, we will find the optimal combination of x and y that maximizes the function, and then we will calculate the optimal value for the function. Here, z is our objective function, and x plus y equals to 56 is our constraint. However, in order to use it for the Lagrange optimization, we need to have the left-hand side equals to 0. To do that, we subtract x from both sides and y from both sides. So here we obtain x minus x is 0 and y minus y is 0. So 0 is equals to 56 minus x minus y. So this is the restriction that we need, which is equals to 0. Now let's set the Lagrange function. And remember, the Lagrange function is equals to the objective function minus the Lagrange multiplier times the restriction. But here, the restriction must be equals to 0. So in that sense, we are subtracting 0 from the objective function, which means that optimizing the Lagrange function is the same as optimizing the objective function. So now let's plug the values for the Lagrange function. And the Lagrange function will be a function of x, y, and the new variable lambda. Here the objective function is this. So this is 4x squared plus 3xy plus 6y squared minus lambda times, here we have the restriction, which is 56 minus x minus y. And notice that this must be always equals to 0. Now our second step is to find the first order conditions for each of the variables. Because we have 3 variables, we will have 3 order conditions. The first one with respect to x, then with respect to y, and finally with respect to lambda. With respect to x, this is 8x plus, here the constant part will be 3y, times the derivative of x with respect to x is simply 1, and then minus lambda times the derivative of these expressions with respect to x is simply minus 1. And this is because 56 is a constant and y does not contain x. So the only variable part here is minus x, and the derivative of that is minus 1. And we set this equals to 0. Now let's do the partial of the Lagrange with respect to y. So the first term is 0. The second term is 3x, which is the constant part, times the derivative of y with respect to y is 1, plus derivative of 6y squared is 12y, minus lambda, and then the derivative of this parenthesis with respect to y is also minus 1. And because this is the first order conditions, we set this partial derivative equals to 0. And finally, we take the derivative with respect to lambda. Here it will be minus 1 times 56 minus x minus y, and this must be equals to 0. And now let's organize it. So this is going to be 8x plus 3y, and then this is plus lambda, and it goes here, plus lambda equals 0. Here we have 3x plus 12y plus lambda equals 0. Here we can multiply by minus 1, so this cancels out, and we have here, or actually what we can do, which is easier, is notice here, I will write it down. This is minus 56 plus x plus y equals 0. So we can arrange it as x plus y equals 56, which is, in other words, the original way that was written here as the constraint. So this means that our procedure was correct. Now, why I put it in that specific order? If you recall, all of these terms are linear, and we have a 3 by 3 matrix because we have 3 equations and 3 unknowns. So for this specific case, when everything is linear, we will use the Cramer's rule. In order to use the Cramer's rule, we need to first pass everything as matrices. Remember from the previous chapters that we need to have the coefficient matrix times the vector of unknowns and has to be equals to the vector of constants. So in this case, we have 3 variables, which are x, y, and lambda. Then our vector of coefficients is going to be a 3 by 3. And are the coefficients that are on the left side, which are 8, 3, 1, 3, 12, 1, 1, 1, 0. And then the vector of constants. Notice something important, and you have to be very careful. Do not forget to move the constant when you take the partial derivative with respect to lambda to the right hand side. That is a very common mistake, so please be careful with that. Because if not, if you continue having it here, you will not be able to use the Cramer's rule. So here we have the constants on the right hand side, which are 0, 0, 56. And now, because we have 3 unknowns, we will have 3 submatrices. A1 is simply the same as the A matrix, except that the first column will be replaced with the B vector. In the case of A sub 2, is the same as the A matrix, except that the second column is replaced by the B vector. And finally, for the case of A sub 3, is the last column the one that is replaced. And remember that because we have these submatrices, in order to obtain the value of the first element, which is x, will be the determinant of the matrix A in the denominator and the determinant of A sub 1 in the numerator. For the case of y, is the second term, so we use the A sub 2, and for the case of lambda, is the third submatrix. So let's find on another paper the determinants of A sub 1, A sub 2, and A sub 3. Remember that in order to take the determinant of a 3 by 3 matrix, we need to copy the first two columns on the right hand side of the matrix. So let's do that to all the matrices. Now let's start with the multiplications of the main diagonal. So here we have 8 times 12 times 0 is 0, plus 3 times 1 is 3, plus 1 times 3 times 1 is also 3. So this is equals to 6. For the case of the anti-diagonals, we have 1 times 12 times 1 is 12, plus 1 times 1 times 8 is 8, plus 0 times 3 times 3 is 0. So this is equals to 20. This means that the determinant of A is 6 minus 20 is minus 14. Let's continue now with A sub 1. 0 times 12 times 0 is 0, plus 3 times 1 times 56 is 168, plus 1 times 0 times 1 is 0. So this is equals to 168. Now let's continue with the anti-diagonals. 56 times 12 times 1 is 672, plus 1 times 1 times 0 is 0, plus 0 times 0 times 3 is 0. So this is equals to 672, which means that the determinant of A sub 1 is simply minus 504. Let's continue with A sub 2. 8 times 0 times 0 is 0, plus 8 times 1 is 0, plus 1 times 3 times 56 is 168. Now let's multiply the anti-diagonals. So here we have 1 times 0 times 1 is 0 plus here we have 56 times 1 times 8. That is 448 plus 0 times 3 times 0 is 0. This means that the determinant of a sub 2 is equals to minus 280. Now let's go to a sub 3. 8 times 12 times 56 is equals to 5,376. 3 times 0 times 1 is 0 plus 0 times 3 times 1 is also 0. Then 1 times 12 times 0 is 0 plus 1 times 0 times 8 is 0 plus 56 times 3 times 3 is equals to 504. This means that the determinant of a sub 3 is equals to 4,872. So now we have all the determinants. Now we can obtain our optimal values. For x, for example, will be minus 504 divided by minus 14. For y will be minus 280 divided by, again, minus 14. And for a sub 3 is 4,872 divided by minus 14. This means that the optimal value for x is equals to 36, for y is equals to 20, and for lambda, the optimal value is minus 348. The important ones here for now are x and y. Our last step is to find the optimal value of the function. Remember that the function was equals to 4x squared plus 3xy plus 6y squared. So here we need to replace the value of x equals 36 and y equals 20. So this is 4 times 36 squared plus 3 times 36 times 20 plus 6 times 20 squared. The optimal value of z is 9,744. So this is the optimal value for the objective.